So thanks all, everyone. I hope you had a great conference. I did, certainly. And today I'm going to present you understanding stream table duality using Apache Kafka, Flink SQL, and Debezium format. So most of content of my talk will be based on a book, Streaming Systems, which was written by the Tyler Akidao, Slava Cherniak, and Rowan Lux. It's a really nice book if you are learning about streaming systems. And most of my talk will be based on Chapter 6 and Chapter 9. There is a nice quote from the book. Julian Haidt is fond of saying streams are like derivatives of tables and tables are integrals of streams. I think it's a good quote to set the stage for my talk. And Julian Haidt is one of the lead developers of the Apache Calcite project, and he was also a pioneer who started the Streaming SQL initiative together with Apache Flink, Apache Beam, and Apache Apex communities. So my background is databases. So in my previous jobs, I worked in highly analytical OLAP databases. So I know about the tables, columns, unique keys, and doing batch-based processing. And recently, I joined Ferverica, which is a company originally created Apache Flink project, and I started my streaming journey there. And apparently, there is a duality between the two, which means one can be transformed or derived from the other, or vice versa. And another quote from the book is, tables and streams are two sides of the same coin. And one other powerful thing is, of course, we know that databases have interface to the SQL. You can use SQL to do your to run your queries, and apparently you can also run SQL on top of the streaming data, which I find very powerful. So, what kind of transformations we can apply? So we can. From the streams, we can produce a table, which is an aggregation of events over time. The result of this aggregation stored as a table, which produces a table. And likewise, we can produce streams from the tables. If we observe the changes happening to the table over time, all those changes can be seen as a stream. But we should also look them individually, separate from each other. Tables are resting place for data which accumulate over time and could be observed. And tables represent data at rest. And streams, on the other hand, capture the movement of the data, which as the changes applied to the table. So streams represent data which are in motion. So to see how those transformations happen, we can have an example where we have such a data processing pipeline, where we read data from some source, in this case, bounded data from a list of files. And we read that data and send it as a stream to the next operator, which applies a map transformation, parses the input into some internal representation. And that also sends the stream to the next operator, which applies a key-by operator, aggregation per key, which brings the stream of data into rest to create a table for the summation. And once all the aggregation is calculated, the results will be sent again as a stream to the next operator. So we can represent it, all those flow of the data either as stream or table. So for example, once we read the data from the files, they are propagated as a stream to the next operator. We apply a map transformation on a stream, which again produces a stream. And by the grouping operation, we bring all the stream data to a rest to do aggregation. And in this example, at some point, there will be an indicator, like end of input, end of file, or last record. And once that indicator received on aggregation operators, they will send the results to the next operator as a stream, which, again, sync can write to the database or file or another third-party system. But on that example, we looked into the bounded data. So our input was list of files or a table or a database, which has some bounded end of input indicator. And when we do the key by summation operation, which we bring the stream into a table, we had that end of result indicator, which again we sent the result of summation as a stream to the next operator. If we have unbounded data, like stream, what kind of triggers we can use so that we can send again our aggregation result into a motion as a stream into the next operator. And for that, we need to look into two new concepts in a streaming world. One is the windowing. So it's slicing of the data in some temporal boundaries. So three approaches are fixed windows. So a window with a size, begin and end. And another approach is sliding window with the size and some interval. If the interval is less than the size, of course, we will have the overlapping windows. And the third one is a session windows with some gaps in between. Session windows can be useful to do some user behavior analytics. For example, a user watching YouTube videos during the day. Another concept is watermarks. It is so, for example, when we have a window, and here I am, my examples based on a window which is on a event time boundaries. And when we do some aggregation on that window, we want to know if all the events which belong to that window did the summation or computation all the events which belong to that window. And watermarks can be used for that. They are special events in a streaming system which indicate the progress of time with monotonic increasing timestamp. So, for example, if we have a window operator which does the aggregation from 10 a.m. in the morning and 11 a.m. in the morning in event time, so once the window operator receives a watermark with time t, which is after the window end, that window operator can have some confidence with high probability that no more data will arrive with the event time which is less than that time of the watermark. So watermarks can be used a trigger for such window operations to set the results to the next operator. So coming back to our data streaming pipeline, now we have unbounded data. And on the key by operator, we have now additional dimension, a window. We do a key by summation on some window. And here we will use the watermark, which will trigger the result of the window as a stream to the next operator. So it will be again similar. Now on the key by summation, we have a window with a 2-minute size. And once we create a table from the stream on key by operator, at some point it will receive a watermark after the 2-minute event size. And then once the watermark is received, they can send their results as a stream to the next operator. And if you look into this example, the watermarks will be received on each window on a different processing time. So the results will be sent to the next operator in different time compared to the bounded, where the results were sent at the same time when they received end of the input indicator. Of course, there could be a late arriving data. The watermark in streaming systems are some kind of heuristic. And for example, in Apache SQL, the late arriving data will be dropped. But if you are using DataStream API, you can send the late arriving data to a different stream. So let's summarize. So we have some operations which are applied on a stream or table and produce a stream or table. We have a non-grouping operations which are filter, map, which apply to the stream and produce the stream. And we have a grouping operations such as group by, key by, or reduce by, which bring the stream of data into a table. And windowing in unbounded datasets could be used to add the dimension of the event time to the grouping operation. Similarly, we can set the result of the table or aggregation using ungrouping operation or triggers. And for unbounded data, we had the end of the input or last record kind of trigger, but watermarks can be used for the unbounded data to have some notion of the completeness for the window. And of course, table cannot be, there's no operation which transforms table into a table, and because table cannot go from being rest back into rest without going into a motion. Okay, now I will speak about the streaming SQL, mainly in the context of the Apache Flink. I found this very powerful because any data processing pipeline which don't have a SQL, in my opinion, is incomplete. So in Apache Flink, all the changes observed on a table produce a stream, and that stream is called a changelog stream. And you can convert this changelog stream into a table, and in Apache Flink, we call this a dynamic table. And all the operations in the Flink, like sources, map, filter, group by, sync, work on this changelog stream. And you can run the SQL queries on top of the dynamic table, which is called continuous queries. They are never ending, and the results will be updated to reflect any change in your input data. In continuous results will be dynamically updated when you have a change in your input data. Another thing we should look is the changelog stream has a mode. So if you are only inserting the records into a dynamic table, it will have the insert mode, which is indicated by +I. And if you do the updates, it will be indicated by 2 modes, update before and update after. Update before provides the previous result, but update after will have the new result of the update operation. And of course, the delete operation, which is indicated by the -D. So for example, if we have a table like this with the name and zip code, so when we add a new record to the table, it will be indicated with +I. And if we update that record, it will have 2 events, which is update before with the previous value and update after with the new value. And with the delete, you will have another event. And you can imagine this table based on some streams as such. So we have the insert event and then update event with update before and update after, and finally the delete event. And in Flink, you can create, in Flink SQL, you can create a table on top of your data source, and you can define using a connector which kind of a source is that, and each source comes with implicit changelog mode. For example, file system connector comes with the insert mode, and Kafka with, again, insert mode, but Kafka observed with insert and delete mode. And if you use Kafka connector with the Debezium format, you get all the changelog modes insert, update before, update after, and delete. So before the demo, let's also talk about the change data capture. CDC is basically a technique or pattern for tracking or capturing the changes applied to your database over some time. But you can use Debezium to apply your CDC. And the Debezium is not an Apache project, but it's also open source and with the Apache 2 license. So for example, if you have a database, you can use a Debezium to observe all the changes, all the DML queries via the log files. In MySQL, it's called the bin log file. In Postgres, it's a transactional log file. And so with the CDC, you don't have to wait until your database is complete and do some bulk processing. Instead, you can observe all the changes happening to your data in real time and send it into the downstream processing data processing pipelines in real time and do your analytics there. So let's do a demo. So for the demo, I have such a setup. So I will use a Postgres database, and with the transactional logical encoding enabled, I have a Kafka cluster setup with the Debezium, Postgres Debezium connector. And I have an Apache Flink cluster. So for the demo, we will do some updates on a table, a Postgres table, and we will observe with the Kafka consumer all those changes happening to the table. And on Flink SQL, we will run some SQL queries on top of those changes as they arrive on real time. Okay. So I'm not sure if it's how visible is that. Good. Okay, maybe like that. So I already started the Docker-based setup, and let's see, everything is running. And I will create a Postgres Debezium connector and run, create some tables, do some operations. I hope the demo gods are kind to me today. So actually I can show you. So I created a table, added some records into it, did the update, and deleted one record. So now I would like to, so at the moment, all those changes are in a Kafka. So with a Kafka consumer, I can observe those changes. And here I have, so I started one simple terminal consumer, and you can see the Debezium has its own format, but I'm only interested in the operation. So the operation is create, not insert. In Debezium, it's a create. And we added one record with the name and amount and another record. And we did an update on some record. So this is update before the previous value of the record, and then we have an update after the new value of the record. And we did a delete. We deleted one record. So now I would go to the Flink SQL. I think it's job manager. Okay, so I will start my Flink SQL client. And I would like to create a table on top of those changelog streams, which is in Kafka. So for that, we can create a create table. I can run a create table statement. So here I am creating a table with similar columns, and I use Kafka connector with the Debezium format, and I provide a topic and some other settings. And now I can do, for example, a select on this table. So I would expect I see the current state of the table. So yeah, 2 records. I don't know why you can. So is it better? Yeah. So now let's add some more records to the Postgres database. Okay, so let me quickly go to the Postgres. So, for example, we can insert a new record. I think ID, the name, and the amount, and the values. So, for example, 41. And let's add back the Bob with some amount. So, when I add this record on the left side, on our Kafka consumer, I would expect a new event coming with a crate. And here I would expect to see a new record on a select query. So, yeah, that's a new changelog in a Kafka, and now we have a continuous query on Flink SQL side updated once the input is changed. But what we can do is we can also do some aggregation. So, for example, and then let's group by name. Okay, let's add another record for the Bob with the new ID. So now, when I insert that record on the other side, on the consumer, we are expecting to see a new insert, like new create record. But here on the Bob's summation should be 20. Yeah. And continuous query on Flink SQL side updated once the input changed. And similarly, we can do a delete or update. Let's set amount to 20 for the Bob, the last one. And yeah, as you can see, the continuous query updated the summation to 30. And now we can do a delete just for completeness. Let's remove the last the ID 42, and then we expect on the SQL query the Bob's amount to be 10, and on the other side we expect to see the delete operation. Yeah, an operation is delete. Previously we had on update on the Kafka consumer side we had the update before and update after. And one last thing, so a moment, I want to show another thing. So we can also on Flink side observe the changelog modes. So if I do the select query here, it should also show that all the operations we did. For example, we have the insert several times, and then update with the update before and update after, and delete and insert and update. So that's it for the demo, and now I will talk about the Flink CDC. It's Flink CDC. Flink offers a connector, CDC-based connectors, which come with all the changelog modes. And with that, you don't have to, if you don't have a Kafka cluster, you can directly observe changes on your database and do your enrichment in the Flink SQL site and send the results to the third-party systems. And Flink CDC was recently adopted into the Flink project, so you can build your own ETL pipelines in real time to observe the changes coming to the source systems and do some enrichment, filtering, joining, and send them to the BI tools, data warehouse, or database. So to conclude, we learned about the stream table duality and how they are transformed with each other, and how the SQL engines use this concept to run the continuous query, and we tie it all together using Debezium for CDC with Apache Kafka and Apache Flink. So these are resources. It wouldn't be possible without these people. And one last thing, also this year we are having Flink Forward in Berlin, which is a 10 years of the Apache Flink project. So everyone is invited to join that. So thanks a lot, and if you have questions, I'm happy to answer.